Hello, in this lecture I will talk about mathematical induction. Mathematical induction is actually a logical method to prove that a statement, a claim, or an equation is true for all natural numbers. And a natural number is a positive number that is also integer. That is to say 1, 2, 3, 4, 5, etc. So we have actually, as I already said, if we want to prove that a statement, an equation, or a claim is true for all the natural numbers, we use mathematical induction. And in mathematical induction, we have two stages. The first stage, we actually check if the statement is true for n that equals to 1. And then if it is true for n equals to 1, then we will go to the second stage. And in the second stage, actually, we will assume that the statement or the equation or the claim is true for n. That is the induction's hypothesis. And from that assumption, we will rely on that assumption in order to prove that the statement is true for n plus 1. So we will have two equations. The first equation is the induction's assumption or induction hypothesis that the statement is true for n. And the second expression that we must prove is that the statement is true for n plus 1, and we will prove it by relying on the assumption that it is true for n. Okay, so now I will explain the logic behind the mathematical induction. Actually, we have already proved in the first stage that the statement, the equation, or the claim is true for n that equals to 1. So we know for sure that the statement is true for n that equals to 1, and then in the second stage, we actually proved that in general, if the statement is true for n, then it must be true for n plus 1 also. So now we know for sure that the statement is true for n that equals to 1, because we checked that it is actually equals for n plus 1. We actually revealed that it is indeed true for n that equals to 1, so we're sure that it is equals for n that equals to 1, and according to our general proof that if it is true for n, it must be true for n plus 1, we can say that we know for sure that it is true for n that equals to 1. And from our general proof, it must be true for 1 plus 1. That is to say, it must be true for 2, n equals to 2. And now, then we will repeat on the same process. Again, we will say that we know now for sure that the statement is true for n that equals to 2. And from the general proof that if it is true for n, it must be true for n plus 1, we can say that we know that it is true for n that equals to 2, and according to our general proof, it must be true for n plus 1, that is to say for 2 plus 1. So we know that it is true for 3. And now again we will repeat on the same process, and we will say that if it is true for 3 according to our general proof, it must be true for 4, and so on and so on. Okay, so in this way we actually proved that the statement is true for all natural numbers. Okay, so in order to clarify the topic, I will give you 2 examples. We will start with the first example. It is actually one plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So we must prove this statement or equation or claim for all the natural numbers. So we will start with the first stage. That is to say, we will check the statement for n that equals to 1. Okay. So in the left side of the equation we have n equals to 1, so it is 1. And in the right side of the equation we have n times n plus 1 divided by 2. N is equals to 1, so it is 1 times 1 plus 1, all divided by 2, equals to 1 times 1 plus 1 is 2, divided by 2, 1 times 2 is 2, all divided by 2, 2 divided by 2 is 1, so we actually get that 1 equals to 1. So we passed the first test, and we can say that this statement is true for n that equals to 1. Okay, 1 equals to 1. Okay, now we will actually move to the second stage. That is to say, we will assume that the statement is true for n. That will be our first expression or equation, and then we will prove the statement for n plus 1 by relying on our assumption that it is true for n. So the first equation or expression will be the actually induction's hypothesis or assumption that the statement is true for n. That is to say, 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So the first equation is actually the induction's hypothesis. We assume that this statement is true for n. And now we will rely on this assumption in order to prove that this statement is true for n plus 1. So we will write second equation for this statement for n plus 1. So it will be 1 plus 2 plus 3 plus n plus 1, because we want to prove that this statement is true for n plus 1. And actually, in the right side of the equation, we have n times n plus 1 divided by 2. It is in the original statement. And in the second equation, we want to prove that this statement is true for n plus 1. So wherever it is written n in the original statement, we will write n plus 1. So it will be, if it is n times n plus 1, it will be n plus 1 times, here it is n, so we write n plus 1. Here it is n, so we write n plus 1 plus 1 all divided by 2. So we actually, in the second stage, assume that this statement is true for n, that is to say 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. And that is actually the induction's hypothesis, and we will rely on this assumption in order to prove that this statement is true for n plus 1. That is to say 1 plus 2 plus 3 plus n plus n plus 1 equals to n plus 1 times n plus 1 plus 1 divided by 2. So wherever it is written n in the original equation, in the original statement, we will write n plus 1 because we want to prove that the statement is true for n plus 1. Okay, so as I have already told you, we will rely on the assumption of the induction in order to prove that the statement is also true for n plus 1. So if we look in the second equation on this expression that is in the right color, we can say that this is equals to the right side or the left side of equation 1. Yes, it is exactly as the left side of equation 1. This equals to this, and in equation 1, this expression 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So we can substitute the expression that is in the green color by n times n divided by 2, because these two expressions equal to each other. Okay, so we will actually do the substitution now for the two expressions that are equal to each other. So instead 1 plus 2 plus 3 plus n, we will write n times n plus 1 all divided by 2. So plus here in the second expression or equation is here as n plus 1, so we will leave it as it is. We will copy it to the second expression. Yes, in the this second expression we only substituted the expression in the green color by n times n plus 1 divided by 2, because they are equal to each other according to our assumption, according to expression 1, that is induction assumption or induction hypothesis. They are equal to each other, so we can substitute the expression in the green color by n times n plus 1 divided by 2. And next, in the second expression, we have n plus 1, so we will copy it as it is. And then in the left side of equation 2, we have n plus 1 times n plus 1 plus 1. So it is n plus 1 plus 1 is n plus 2. So in total we have n plus 1 times n plus 2 and all divided by 2. So you can see it, the second expression that we have to prove that this is true. We have n times n plus 1 divided by 2, because we substituted 1 plus 2 plus 3 plus n by this expression, because they equal to each other, then we have plus n plus 1, we copied it as it is, and all equals to n plus 1 times n plus 1 plus 1. And n plus 1 plus 1 is actually n plus 2. So in total we have in the right side of the equation n plus 1 times n plus 2 all divided by 2. So in this second equation that we have to prove that it is true, we can divide both sides of the equation by n plus 1. And we can divide by n plus 1 because it can never be 0, because n is a natural number. Okay, so we will divide both sides of the equation by n plus 1, and then we will get that the second expression, actually that we have to prove that it is true, it is actually n divided by 2 plus 1 equals to n divided by 2. So after we divide both sides of the equation by n plus 1, we get that n times n plus 1 divided by 2 is actually n divided by 2, and n plus 1 divided by n plus 1 is 1, so we will add 1, and all equals to n plus 1 times n plus 2 divided by 2. After we divide it by n plus 1, actually it equals to n plus 2 divided by 2. So here we can part the n plus 2 to two parts. Okay, so we will write that n plus 2 plus n divided by 2 plus 1 equals to n divided by 2 plus 2 divided by 2. So after we actually parted n plus 2 to two parts, we got that n divided by 2 plus 2 divided by 2, and 2 divided by 2 is 1, so we will write it down. So we actually got identity. The right side of the equation equals to the left side of the equation. So we actually proved that the second equation or expression is true. And that's what we needed to prove. And actually in this way we proved that this expression is true for all the natural numbers. Why? Because we proved it for n that equals to 1 in the first stage, and then in the second stage we proved that if it is equal to 1, it must be, if it is true for n, it must be true for n plus 1. So we can say that we know that it is true for n that equals to 1, and then according to our general prove that if it is true for n, it must be true for n plus 1, we know that it is true for n that equals to 1, and from that we can deduce that it must be true for n that equals to 2. And from the fact that we know that this expression is true for n that equals to 2, it must be true for n that equals to 2 plus 1, that is to say to n that equals to 3, according to our general proof, that if it is true for n, it must be true also for n plus 1. So we will repeat on this process again and again, and in this way we actually proved that this statement is true for all the natural numbers. Okay, so now we will we'll give you another example. The second example will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So we must prove that this statement is true for all the natural numbers. So we will start with the first stage, that is to say, we will prove that this statement is true for n that equals to 1. So in the right side of the equation, we have 1 to the power of 3 equals, in the left side of the equation, we have n squared times n plus 1 squared divided by 2, and we know that n equals to 1, so it is actually n squared, 1 squared times 1 plus 1 squared, and all divided by 4. And here 1 to the power of 3 is 1, equals to 1 to the power of 1 square is 1, and 1 plus 1 is 2, 2 square is 4, all divided by 4. 1 equals to 1 times 4 is 4 divided by 4, or 1 equals to 1. So we actually proved that this statement is true for n that equals to 1. Okay? We proved that this statement is true for n that equals to 1. So now we will move to the second stage. That is to say, we will assume that this statement is true for n, and we will rely on that assumption in order to prove that this statement is also true for n plus 1. So we will assume that this statement is true for n, that is to say 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So this will be the induction's hypothesis or induction's assumption that the statement is true for n, and we will rely on this assumption in order to prove that this statement is true for n plus 1. That is to say, n to the power of 3 plus 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. So we will prove that this statement is true for n to the will prove that this statement is true for n plus 1. So we will go until 1, 2, 3 until n plus 1. So the next, after n to the power of 3, we will have n plus 1 to the power of 3 equals to, in the original expression we have n squared times n plus 1 squared divided by 4. So, and we want to prove that this statement is true for n plus 1. So wherever it is written n, we will write n plus 1 because we want to prove it for n plus 1. So instead of n, we will write n plus 1 square times n plus 1 plus 1. Wait, twice plus 1 square, all divided by 4. So we assume actually that this statement is true for n. That is the induction's hypothesis or induction's assumption, and we will prove that this statement is true for n plus 1. That is the second equation. Okay, so we will repeat on the same process. We will prove the second equation by actually substituting this expression by n squared times n plus 1 squared divided by 2, because they are equal to each other. This is equal to this, and therefore this equals also to this. Okay, so we can substitute this expression in the green color by this expression because they are equal to each other. So we will do now the substitution. So here, in the second expression that we have to prove, we actually substituted the expression that is in the green color by n squared times n plus 1 squared divided by 4, because according to our assumption, that is the induction hypothesis, they are equal to each other. Okay, this is the induction hypothesis that says that these two expressions are equals to each other. So we actually substituted the expression in the green color by this expression, because they are equal to each other. And then we have also plus n plus 1 to the power of 3, so we copied it as it is, and then all equals to n plus 1 squared times n plus 1 plus 1 is n plus 2, so it is actually n plus 2 squared, like here, and all divided by 4. Okay, so now we can divide both sides of the equation by n plus 1 squared, because we have this expression in both sides of the equation. So we'll do it now. So here, after we divided both sides of the equation by n plus 1 squared, actually this expression divided by n plus 1 squared equals to n squared divided by 4, and n plus 1 to the power of 3 divided by n plus 1 to the power of 2 equals to n plus 1, and in the right side of the equation we have n plus 1 times n plus 2 divided by 4, so we divide it by n plus 2 squared, so it is equal to, oh, I made a mistake, 1 minute. Okay. So we divided both sides of the equation by n plus 1 squared, so what is left is it is equal to n plus 2 squared divided by 4. So here we can multiply both sides of the equation by 4. So after we multiply both sides of the equation by 4, we got that n squared divided by 4 times 4 equals to n squared, and n plus 1 times 4 equals to 4 n plus 1, and n plus 2 squared divided by 4 times 4 equals to n plus 2 squared. So now we will open the brackets of both sides of the equation, and we will get actually n squared plus 4n plus 4 equals to n square plus 4n plus 4. So here, after we opened the brackets, we got that here it is n square. We copied it as it is, and 4 times n plus 1 equals to 4n plus 4, and n plus 2 square equals to, according to our rule, that a plus b square equals to a square plus 2ab plus b square. It is equals to n square. 2ab is 2 times 2n, so it is 4n, and 2 square is 4, so in total we got that it is n square plus 4n plus 4. So we have here identity. The left side of the equation equals to the right side of the equation, and we can say that we proved that if the expression, if this expression is true, if this expression is true for n, then it must be true for n plus 1. And in this way we actually proved that this expression is true for all the natural numbers. Why? Because we proved we have already proved that this expression is true for n that equals to 1. And we, in the first stage, and in the second stage, we proved that if it is true for n, it must be true for n plus 1. And we proved that it is true for n because we checked that it is true for n that equals to 1. And from the general proof that if it is true for n, it must be true for n plus 1, we can say, because of the fact that it is true for 1, n equals to 1, it must be true for 1 plus 1 also. That is 2. And then when we know that it is true for n that equals to 2, it must be true for n that equals to 2 plus 1, according to our general proof that if it is true for n, it must be true for n plus 1 also. And now that we know that it is true for 3, it must be also true for 4, according to our general assumption. So we will repeat on this stage, on this process again and again, and in this way we actually proved that this expression or equation is true for all the natural numbers. Okay? So we can summarize the lecture and say that mathematical induction is a logical method to prove that a statement or a claim or an equation is true for all the natural numbers. A natural number is a positive number that is also integer, like 1, 2, 3, 4, and so on. And we, when we prove a statement by mathematical induction, we actually make two stages. In the first stage, we check if the statement is true for n that equals to 1, and if it is indeed true for n that equals to 1, then we will move to the second stage. That is to say, we will assume that the expression or the statement or the equation is true for n, and from that assumption we will prove that is also true for n plus 1. And after we proved that it must, if it is true for n, it must be true for n plus 1, we can say actually that we proved that the expression or the statement or the equation is true for all the natural numbers. Why? Because we checked that it is true for n that equals to 1, and we in general proved that if it is true for n, it must be true for n plus 1 also. So from that we can deduce that because of the fact that it is true for n that equals to 1, it must be true also for n that equals to 1 plus 1. That is to say, must be true for n that equals to 2. And then we will repeat on the same process. We know for sure that it is true for n that equals to 2. And according to our general proof that if it is true for n, it must be true for n plus 1, we can say, because of the fact that it is true for 2, it must be true for 2 plus 1, that is 3, and so on and so on. And in that way, we actually proved that the statement is true for all the natural numbers. Okay, thank you very much.